Moving on, I'm delighted to introduce our next keynote speaker, Nathan Baker. He's a quantum applications lead at Microsoft, and he's going to share with us a perspective on quantum optimization, unlocking the power of quantum breakthroughs to tackle HP hard challenges. So please join me in welcoming Nathan.
Okay, so thank you very much for the opportunity to present to you all today. I'm going to be covering Microsoft's journey on accelerating scientific discovery with quantum computing, and tell you a little bit about some of the recent announcements and where we're headed at the intersection of high-performance computing, quantum computing, and artificial intelligence. So I'll start with our perspective on quantum computing as a whole. So Microsoft is a platform company, and as you know, if you log into Azure, you have your choice of many different kinds of CPUs, many different kinds of accelerators. Our goal throughout the Microsoft mission is to empower people and organizations to achieve more using whatever tools are most appropriate for their mission. So when we talk about quantum computing, we take a very similar approach. And what I'm going to tell you about today is talking through that quantum computing stack and how we think about each layer of the stack at Microsoft and what technologies we're bringing to bear for that. So the first element on the stack is, of course, the quantum processing unit. And in the same way that we offer many different kinds of CPUs and GPUs, we offer many kinds of quantum processing units. I'm going to focus on a couple different ones today. But in the spirit of platform play with quantum computing, we really do embrace many different kinds of technologies. On top of that is the very important component of error correction. As we all know, qubits are fickle. They don't always do what you tell them to do. You need to bring them together with error correcting codes in order to harness their potential and make them work as reliable qubits. And then finally, applications and services. What do we put on top of these two layers of the stack to enable people to achieve their missions? So I'll start with the quantum computing processing unit component of the stack. And while we do offer many different kinds of processors on the system, given the recent announcements, I wanted to focus on one today, which is the topological superconductor or superconductor. This is the next step on a nearly 20-year journey that Microsoft has undertaken, pursuing topological approaches to quantum computing. It builds on many published successes over the years, and it's something we're very excited about because it represents a commitment to this vision of topological quantum computing, and we're increasingly seeing that commitment translate into real-world devices. And so in particular, when we think about zooming into this, going from the qubit out to what are we going to put inside a dilution refrigerator? How is the world going to use this? We announced just recently the Majorana 1 quantum processing unit. This is powered by that topological core, those topoconductor systems, and it represents our first step toward now making this a commercial reality. We're very excited about this technology because it meets three criteria that we believe are necessary to have a clear path to scaling out quantum computing. In particular, these topological qubits are small, fast, and reliable. What do each of those mean? When we talk about small, as you saw in the previous slide, we're actually able to pack a very large number of qubits into a very small footprint, with the possibility of taking up to 1 million physical qubits and putting them inside a single dilution refrigerator. It's extremely exciting because it means you don't have to worry about the fridge-to-fridge interconnectivity. You have a path to scaling with this hardware. Fast, we're looking at qubits that can be operated on the microsecond time scale with very clear control. And that speaks as well to the reliability. Not only does the qubit have built-in error mitigation through its topological nature, but it's also controlled by digital pulses rather than analog pulses. And that contributes to both the speed and the stability. Now, as I mentioned, this quantum computing journey, this topological quantum computing journey is just one step on a long march that Microsoft has been making for nearly 20 years. And the announcement over the past week or so has built on many different successes before it. The first of which was announced last year in a Physical Review B article that showed that through a nanowire, in particular a composite of a superconductor and a semiconductor, we were able to demonstrate the passage or the successful implementation of the topological gap protocol, which demonstrated the realization of Majorana zero modes, this new form of matter that we've been talking about, in a nanowire. So this is the basis for topological computing. And it's a very important building block for last week's announcement about the measurement protocol that allows you to actually start to manipulate these Majorana zero modes. So what was published last week was that single-shot parity measurement in these nanowires for measurement-based computing with this topological phase of matter. And it's based on the realization of these Majorana zero modes in this nanowire substrate. So we're very excited about this. Again, it's been a long journey for us, and it's a journey that will continue to evolve. And it represents just one part of how we think about the quantum computing ecosystem at Microsoft. So I want to talk about those other parts now, and I'll move up the stack one level to talk about quantum error correction and computation. Microsoft is interested in reliable quantum computing. Now, we often talk about that in terms of logical qubits, and for that we mean qubits that can do three things. They can detect errors, they can correct those errors, but at the same time they can do computing on the information stored in those qubits. We're not interested in quantum memory. We want to enable quantum computation. And our approach to that, sticking with the platform theme, is by virtualizing out the qubits, by building in a layer of error correction that allows us to deal with many different types of qubits and perform error correction in many different hardware environments. So over the past year, we've had a lot of exciting successes in that error correction pathway. And this also introduces some of our other partners on the quantum computing journey. So back in April, we announced 4 logical qubits. These are reliable qubits that offer the detection, correction, and computation. This was in partnership with Quantinuum and their excellent hardware stack, combined with the work of Microsoft Quantum's error correction team, gave us the ability to demonstrate 4 logical qubits from 30 physical qubits, and then very quickly, only 5 months after, show how to build 12 logical qubits from 56 physical qubits. Very exciting journey with the ion trap hardware. Additionally, last year, starting in November, we announced 28 logical qubits by implementing that qubit virtualization system on top of Atom Computing's neutral atom hardware. And that's a system that actually we talked about in our Ignite event. Satya Nadella used it to introduce this Discovery Suite, our commercial offering that'll start delivery at the end of calendar year 2025, with a path towards 50 logical qubits based on initially the Atom Computing's neutral atom hardware. So it's a very exciting journey, and again, it reflects the Microsoft platform play to this. However, we all know where we need to go, right? And while it's exciting to see, progress from, 4 logical qubits to 28 in the span of only a few months, we know that for commercial impact, for industry impact in quantum computing, we need a path to 1,000 logical qubits or more, which means 1 million physical qubits or more. And again, that's why we were excited about the topological computing announcements over the past couple weeks. We feel that logical qubits are here. You can already start to use them in the system we've been developing, but we can also have a very clear growth path that takes us to 1 million logical qubits to really tackle those industrial challenges. So I want to wrap up here with the last part of the stack, and that's quantum applications and services. So we're interested, obviously, in offering many different kinds of hardware, making sure that those different qubits get virtualized into a system to enable reliable quantum computing. But of course, we want to enable people to solve real-world problems, and that's really where applications and services come in. We're all excited about the prospect of what quantum computing is going to do for applications across many different domains. We've heard a lot about them today and in other presentations. Tremendous opportunity for quantum computing. We've taken a very specific, very focused view on the impact of quantum computing, and we've spent a lot of time thinking about where quantum computing is going to have an impact in the physical sciences. So we've invested a lot of time, effort in realizing that intersection of quantum computing tools with traditional physics-based tools implemented on high-performance computing hardware, together with artificial intelligence to specifically target problems in chemistry and material science. Quantum computing is going to have a broad impact across many domains, but we're really placing our bets in this chemistry and material science domain for our internal application effort. And what does success look like there? If we're able to integrate these three technologies, physics-based models with high-performance computing, artificial intelligence, and quantum computing, what sort of things will we unlock? What comes out the other side? Well, many processes in chemistry and material science involves screening. Looking through millions of different candidates. We had a study last year where we looked at battery materials, 32.5 million battery materials to find one new promising candidate for a battery electrolyte. But those are leaky. Those funnels that we put the screening process through, they have errors built into them. What if we could introduce quantum computing into that process to offer reliable screening with first-time right results, whether we're looking for new drugs or new catalysts or new materials for alloys or for batteries? What if quantum computing can get our accuracy to the point where we're first-time right? We're not wasting time in the lab. We're taking what comes from the computer, making it, testing it, integrating it into products. The second step where we're excited about the promise of quantum computing is providing more direct guidance in how people actually make new materials or make new chemicals that come out of these screening processes. We often think, I'm a computational chemist, that we make something in the lab, it ought to be easy, right? Or we make something on the computer, it ought to be easy, right? We hand it over to the lab, they make, they just put the chemicals together and something shows up. In fact, that process of going from the computer to the lab is very difficult. So what if we can use quantum computing and use these computational tools to provide much more useful and directed guidance about how people make those chemicals in the lab? We enable efficient synthesis of what comes after the reliable screening. And then finally, we're interested in the promise of quantum plus AI for predictive environmental impact. We want to make sure that as we're doing this screening of new chemicals or new materials, we're enabling the more efficient synthesis of them in the lab. We're thinking about the end in mind. We're not creating the world's next generation of forever chemicals because we can model up front the long-term fate and impact of the new materials and chemicals that we design. Again, something that I think we'll see with the integration of these technologies, quantum computing, physics, and AI. So I've talked about those three a lot in combination now. What does it actually look like? How do they fit together? So today, the world has been using physics-based models with high-performance computing for decades, right? One of the biggest workloads on high-performance computing systems involves simulating the laws of nature. And some of those laws of nature involve electrons, which is a quantum mechanical problem. So when we simulate them on classical computers, we often hit a limit. We hit a ceiling for the size of problem that we can solve without making approximations. Because these quantum mechanical problems, when we map them to a classical computer, scale exponentially in problem size. And that means for some chemical or quantum mechanical systems, you have to start to make approximations. But even with those approximations, we've shown the power of using these physics-based methods in combination with artificial intelligence. In particular, we've shown that when you use the training data that comes out of these classical high-performance computing simulations, you can train AI models that operate 1,000 or 2,000 times faster than the original physical models. So it's a tremendous speed up that you get by training AI models based on HPC data. But why did I spend time talking about the limitations of HPC? Turns out that we're training these models on imperfect data. When we train them based on a classical solution to a quantum mechanical problem, we often have to make the approximations, and those approximations can degrade the accuracy of the training data. This leads to problems later on because our AI models, while fast, are only as accurate as the training data. So our view of the intersection of these three technologies is using quantum computing to remove that problem, right? Using quantum computing to fill in the blanks. when the problems get too big for classical systems, rather than making approximations that impact accuracy, we use quantum computers to get that chemical accuracy needed to make reliable predictions. And so that's our view of how these fit together. In addition to continuing to use classical high-performance computing and physics-based models to train AI to accelerate scientific discovery, we introduce quantum computing to not only accelerate chemical scientific discovery, but give it that chemical accuracy that makes it truly predictive. And so putting this all together, we see that intersection of high-performance computing, quantum computing, and artificial intelligence coming together to accelerate scientific discovery. And we're building a product around this. So we've been investing in artificial intelligence in HPC to accelerate scientific discovery for several years now. And that's starting to culminate in a product that we're building that puts these three technologies together and then puts it in the hands of scientists so they can actually use this to solve problems in the lab without becoming experts in each of those individual technologies. The interface for this should look very familiar to anyone who's used Copilot. We recognized early on as we started to introduce sophisticated computational tools to the scientific community that not everyone is the same level of computer nerd as we are. And we needed to find ways to democratize these tools so they could actually give scientists new capabilities to take the lab without forcing them to climb a huge barrier to learn how to use them. So we have this scientist-friendly conversational interface that allows them to go in, interact with an AI, formulate a problem, do initial modeling of the problem, in this case, catalyst discovery, do initial modeling of it on high-performance computing technologies, and then take the results of that and ask the question, which part of this problem needs quantum computing? Where am I introducing errors into this model because I'm taking that quantum mechanical problem, electrons in a molecule, and I'm modeling it with a classical computer? And how do I introduce quantum computing to address those errors? So that's the system we're building out. We've unofficially called it the Discovery Suite, bringing together these different capabilities. And it's actually based on that announcement we made earlier or late last year, a few months ago in November, when we announced the breakthrough of 28 logical qubits derived based on the atom computing, neutral atom technology. And that forms the basis for this commercial offering, where we're bringing the most powerful quantum computer in the world, 50 logical qubits with a clear growth path to 100 logical qubits in a couple of years, and making it available to the world as a commercial offering designed to accelerate scientific discovery. This is a full stack solution. So while the story I told you today is focused on chemistry and material science, we're building this quantum computer to be useful to everyone interested in innovating in the quantum computing space. It offers, of course, the atom computing neutral atom technology as its foundation. It offers that qubit virtualization layer. It also provides an ecosystem bringing in components of AI, classical computing through high-performance computing, and a stack on top of that to develop, optimize, build your own applications, or use the ones that we and our partners are developing in specific domains. So we're very excited about this opportunity to advance quantum computing in different parts of the world. As our CVP, Matthias Treuer, often ends his talk, he talks about impact for all. We want quantum computing to impact industries and scientific communities around the world. And that's why I was so excited to be able to come and talk to you, because we're excited about the opportunity to make UAE a leader and support its journey in leadership in quantum computing. And I was out walking last night, and it's hard to think of a better picture to take than the Museum of the Future to illustrate the opportunity of quantum computing on the region. So thank you very much for the opportunity to share our journey with you, and I'm excited about our opportunities to work together in the future. Thank you.